Hello, I also go with YZ. I'm an associate professor here at School of Computing and AI. On my way here today, actually I was teaching this morning, and on my way here today, I bumped into a homeless guy. And I was having a small chat with him. He was asking a question at a very metacognitive level. He's asking, why are all these people busy on the road? And I told him, from all the great talks you guys give, and I listened yesterday, that all these intelligent agents are apparently lacking clearly certifiable goals. Anyway, so I do computer vision. I define myself as a computer vision researcher. We try to develop visual concept learning or grounding systems that essentially compositional and robust, but I put parentheses over there because a lot of the work is not yet compositional and robust. That leaves quite a lot of open space to do further research and also lifelong learning in a sense that how can we apply them into actual embodied physical robot. So let's start with how we define visual concept grounding, right? That tracks back to the definition of visual recognition. Typically the community, especially the visual recognition and computer vision community, tends to define visual concept grounding as a pattern matching problem, right? So basically, it's still recognized it as a cognitive process, but involves identification of a visible category from previous encounters. Now, whenever you have previous encounters, annotated data. Previous category means classes. So now you can equate visual recognition as a classification problem. But if you really go back to the definition of visual recognition, it's not just identification of a visible category, right? It's actually a definition of a visible concept, not only just from previous encounters, but also from knowledge. Now you may ask, what is actually a concept? We have quite a lot of cognitive science and cognitive modeling people here, so I'll quickly go over the definition of concept. Essentially, not just categories, right? So the concept should also describe the kind of knowledge stored in this concept, the way they are used in agents' cognitive processes, their formats, their acquisition, and their neurolocalizations. Apparently, there's quite a lot of books talking about this. This philosopher from Canada, Edward Moultrie, has this book called Doing Without Concept, essentially arguing categories are not concepts, thus pattern matching is not visual recognition. Now, let me try to use this example to motivate why visual concept grounding is so difficult. If I give you this image to ask you guys to recognize what you see, immediately most of you guys would be able to categorize it as a pair. And there's multiple instances of pairs. Now, the question is, if you ask the intelligent systems, are they eatable or not? Following our common sense knowledge, we can easily infer pairs are eatable. That's our lifelong learning experience. Yes. However, what about this, right? What about rotted pairs? They are still pairs. The category is pairs. The instance is also pair, but their attributes changed. Their attributes changed from healthy pairs to dark pairs. Now, if you ask, are they eatable? Suddenly, the affordance flipped. They are not eatable anymore. I don't know whether any of you guys coming from northeast parts of Asia or Russia, there is a delicacy called frozen pears. So it's still categorized as pears, but dark pears plus frozen attributes. Now, suddenly, when you ask, are they eatable, they become eatable again, right? So how this dynamic composition and evolving of concept in the land of concept learning makes the intelligent system more interesting to study. Now, let's briefly go over, starting from 2000, the history of computer vision community. We are basically really good at defining tasks and also really good at making every task ultimately into a classification problem. However, let's go over to 2000. the task is to check whether AI is able to understand this image and being able to classify it as frozen pairs, right? It's got a classification, ImageNet, ImageNet, and as well as CarTech 101, all these challenges. About 2010, that was the time people start to argue, hey, just classifying them does not truly reflect the visual concept understanding of the system. Why not let's ask the system to generate human-readable descriptions about the images, such as this one, 2 baskets of frozen pears, Northeast Asian common delicacy, kids love them, and then we judge, based on their generated description, how well they capture the concepts about pears, about the concept, the number 2, about its origin, and so on and so on. And around this time, there is another challenge being proposed called VQA. Many of you guys probably have heard about it, visual question answering. Instead of asking the system to generate a sentence, it basically takes in the image as well as the question as the input and test whether the image, whether the AI is able to answer questions such as, are they eatable, correct or not? If they are able to answer them, we are basically saying, hey, sort of we are evaluating how well the system understanding the concept of pair and the attributes of them and how they connect with each other. About 2016, people start to try to adopt all this VQA captioning system onto an embodied agent. So at that time, there's a robotic object search task. Instead of just having a virtual agent, you ask the agent to say, hey, go find the frozen pairs. And depending on how well the agent performs, you judge how well the agent understands the visual concept of pairs and frozen pairs and so on. And then many of you guys probably are very familiar with nowadays, it's getting into the generative era. So instead of challenging the system to recognize, to do discriminative things, we are trying to challenge the system to generate, for example, generate an image of 2 baskets of frozen pears. A lot of the research on concept bed and the related work, which I'm going to go over later, is from my student Maitreya. But if we're looking at the hierarchy or the history of computer vision, we are sort of climbing this cognitive learning theory of Bloom's taxonomy, right? Starting from remember, then goes higher to understand, then try to apply those learned concepts, and then try to analyze to answer visual questions, and try to evaluate. And right now, sort of, we're at the create level, right? If you want to test the agent is truly able to understand the concept, the agent should be able to create, generate images about these concepts. But people may ask, what's next, right? We're already at the top of the pyramid. What's that? What are the remaining challenges? One of the things I argue at a recent talk at CoRL is even with the top of this task, create, we can unroll and create another hierarchies of creation. And many of them are not yet being tackled. And hopefully today's talk, I convince you that they are not yet tackled in the creation and hallucination or generation manner, including pixelic, right? Photorealistic, geometric, spatial relationships, physical, their physical properties, designative, call them out, right? What's the name of them? Communicative, how you have a generated system to communicate with human users, and speculative, how to create a speculative output from AI or language input. So take this, right? 2 baskets of frozen pears. What we can quickly do is we can try out the most up-to-date stable diffusion algorithms. And I actually did that, 2 baskets of frozen pears. What you get is such an image. Right? Many of you guys are starting to laugh. Now we can, the scientific question is how we judge it, right? The concept 2 are there. The concept pairs are there. The concept baskets are there. But where are these 2 pretty ladies coming from? The frozen movie, right? So apparently the system are linking the attribute, the affordance of frozen, linked to the movie Frozen. And in the community, we call it attribute stealing. And this is actually an issue that we are trying to deal with. Another thing is I give this talk at the CoIL, and one of the audiences, robotists, asked, like, now we are using all these generative AI tools to generate data to train robots. Whether these generative AI tools are actually understanding those affordances of objects. So he asked whether you could try carrots after chopping, because consequence is such an important concept in robot manipulation. You need to be able to verify the consequence of the manipulation of the robot. And if you do that, you get, again, misaligned outputs, right? So apparently, the system also not aligned well with the concept of chopped carrots or carrots. That was 2011, right? So inspired by the DARPA Mind-Eye project, we start to think, like, what is missing in visual recognition? That was 2011. We take in the perception space and also create a language agent and use this language agent to further regulate the recognition of the objects and then generate sentences. That's 2011. We're trying to propose image captioning as the task. And you wouldn't be surprised, the language modeling at that time is very, very rudimentary. We used the IBM Model 4. So instead of large language models, you have 712 contexts. At that time, we're only looking at the 4 words context. And one of the previous speaker mentioned, you wouldn't expect agencies and academia to develop systems like GPT-4, GPT-4V. But what I would like to argue that many of this research and development is seeded in academic research. Around that time, quite a lot of work in this domain got basically picked up with the neural communities, this neural talk, right? And then later being picked up to large-scale data set for image and text models, and that leads to, many of you guys are pretty aware nowadays, GPT and large multimodal models as well. Now, the challenge really is how to use and adopt those visual concept learning ideas into lifelong learning. One of the things is lifelong learning, many of you guys probably immediately related to lifelong learning of human agents, right? So I personally actually taught a course at the ASU Lifelong Learning Institute. Essentially, many of the senior citizens are really interested in the development of AI. But wait, what is robot lifelong learning? I would like to argue, in order to enable robot lifelong learning, we need to first enable automatic evaluation of the agent's its own capabilities, especially in the context of generative AI. So in the remaining of the time, I would like to quickly go over some of our recent work in this domain, how to essentially automatically evaluate T2I models and how well they actually captures the concepts of many. For example, in this work, we are basically proposing to evaluate and properly calculate how well T2I models understand a concept called spatial relationships, right? Spatial relationships are such an important concept. Quite a lot of robotic applications, including manipulation, navigation, direction, and human AI interactions relies on a good understanding of spatial relationships. But does these T2I models actually generate accurate spatial relationships? Apparently not, right? So that was early 2023. We tested quite a lot of those prompts, including a chair above a knife, a teddy bear below a bed, all the generated images still having the teddy bear above the bed, right? So now that leads to the question, how can we create evaluation benchmark as well as an automatic evaluation method to benchmarking spatial relationships, this critical concept that is needed for intelligent agents to do automatic things. That leads to our proposed Visor challenge and spatial relationship challenge data set. With this intuition, the follow-up work is very straightforward, right? So we create a pair of prompts as well as output. And all these prompts are essentially auto-generated from MS COCO data set and from a template to have object A, a specific relationship, and object B. For example, we create a microwave to the left of the sink, a donut above an airplane, all these prompts. With that, what you can do is you can automatically create all these prompts and use it to test the T2I models. Other than all the prompts data set, we also need an automatic evaluation matrix. In this sense, we basically follow the concept that existing matrix fail to cover spatial relationships for evaluation. We propose to use object recognition as a way to automatically evaluate how well the generated content actually reflect the object 1, object 2, and their relationship. And based on that, we'll create an evaluation matrix called Visor. So with that evaluation matrix and benchmark at hand, we were like having a ruler. Now we can essentially test, at that time, a few of those state-of-the-art text-to-image models. And apparently, DALL-E 2 has the highest Visor score. Here are a few of the results that we are able to visually comprehend as well as evaluate. Now, what are the remaining challenges, right? So from the left, we can see that vision T2I models still have challenge to generate content that honor the spatial relationship well. And on the right, we are showing that a lot of the vision language alignment models does not perform well understanding spatial relationship as well. For example, click model, when you're pairing it with this image and a sentence, a backpack below a train, you have a very high click score. But if you switch the text to a backpack above a train, it still have a high click score, actually a higher click score. So apparently not reflecting the actual semantic meaning of the image as well. Since the presentation of Visor, we have observed some of the recent work has already adopted Visor as the automatic evaluation matrix, including the early experiments with GPT-4 and another paper from Oxford using Visor to do the evaluation. And following this insight, we are actually developing next generation or improved T2I models. Here is a kind of teaser output. We're showing that our model can honor the spatial relationship better than the other models. Now, we just talked about spatial relationship. How about other concepts? So that leads us to continue with this line of research, how to create evaluation methodologies as well as benchmarks to test concept learning for text-to-image generative models. In this work, we call it concept bed. Instead of texting a concept directly, for example, if I want the AI to understand this specific kind of bird, basically you can test this, a photo of this kind of bird, and judge whether the generated content is essentially reflecting this kind of bird. However, what we can do is we can add on all the composed prompts as well. For example, if I say, hey, the system understands the concept of train, then the system should be able to also understand the train on the track, or train following another train, things like that. So what essentially we do is create a bunch of composed concepts, including a photo of V, this abstract concept, V flying in the sky, 2V sitting on a tree branch, extra, extra, extra. How to create them? This is a combination of all the existing curated data set, including domain, objects, attributes, and then we start to basically emulate all the combinations, including V with red feathers, V's ears are up, relationship, V has fish in the mouth, V is sitting in a bucket, actions, V is licking herself, V is running at the beach, and counting 2 V's sitting together, and so on and so on. In total, we have about 8,000 prompts as the prompts data set to test the T2I models. Now, the next challenge is how to create an automatic evaluation method to basically judge how well this combined or composed concept are essentially being captured by the T2I models. In this case, we propose concept confidence deviation task. Essentially, in this figure, we're showing that the concept that being learned and asked to learn is art painting of a dog, right? And the model with the original ground truth and the customer diffusion approach is being plotted here. Original ground truth can recognize the generated content very well, and the customer diffusion approach generated image are basically having a distribution over there. So CCT essentially calculates the deviation between these two distributions as a way to judge how well the image-to-text models are essentially being able to capture the concept of art painting of a dog as a target prompt. So with that benchmark and the matrix at hand, we are essentially being able to evaluate and tell which model is good at doing which level of composition, as well as how robust they are. In this case, we're showing that Dream Boost is performing extremely well on domains, and customer diffusion is doing great at objects level combinations. And fine-grained level attributes combinations, we're also showing that customer diffusion is performing the better. Now, the next question is how the evaluation matrix that we proposed aligns well with human judgment, right? So the question is whether the automatic evaluation essentially reflect the human judgment of how well these images are being generated. And we show that from the experiment, we show that our evaluation matrix essentially aligns very well with human scores, better than the other evaluation matrix in both domains, object combinations, and as well compositional of the prompts. Here's a few of qualitative results. As you can see, Dream Boost can generate image such as this specific kind of V, which is the specific kind of birds, learned concept flying in the sky very naturally, but textual inversion essentially put a bird in the sky, which is not capturing the action flying very well in the space. Following this benchmarking and evaluation, we are continuing developing tools that essentially can honor the attributes as well as the composed prompts better. Here is another teaser. This work is still under review, but we are showing that our model with smaller parameters, much smaller number of parameters, can generate images such as black apples in the basket, reflecting the text prompt better than the other models. All right, so with that being said, I would like to have an open discussion and happy to take any questions, and following some of the remain the challenge in generation. Yes, please.